I have a battery connected to a bulb via a switch. I close the switch, the bulb glows. Open, bulb doesn't glow. Close, bulb glows. No surprise over there. But now let's attach a coil wrapped around some metal in series with the bulb and see what happens. Ready? 3, 2, 1, close. Ooh. Now we see the bulb takes some time to glow. Why is that? Well, let's find out. Wait, did you see that? Seriously, what is happening? So with the coil in series, we saw that when we close the switch, the bulb takes some time to glow to its full brightness. From this, we can infer that the current takes some time to grow to its max value, the value given by Ohm's law. Maybe 1 ampere, let's say that's the maximum value. Which means the coil is for some reason delaying, it's slowing the rise of the current. But why is it doing that? Well, let's investigate. If you pause the animation over here, we know that there is some current running in the circuit. It's not maximum value yet, but there is some current. And that current is of course going through the coil. And we've seen when we have current circulating through some coil, it generates a magnetic field. We've seen this enough number of times now. Now what's interesting over here is that this current is increasing. Remember, we are not yet at the max value. We have paused the animation. The current is going to increase, which means the magnetic field that is produced over here also tends to increase. Ooh, this means the flux is increasing. And we know from Faraday's law that whenever there is a change in the flux, the coil will induce an EMF trying to oppose that change. So over here in this coil, there will be an EMF induced opposing that change in flux. Okay, that's a lot to take in. So let's slowly write this down. So what we're seeing at this moment is that there is a changing current. Let's call it DI or delta I. Because of that changing current, because current is producing magnetic field and there is a magnetic flux, there is a changing flux over here. The flux is changing. And we know from Faraday's law that that changing flux causes the coil to produce or induce an EMF, and that EMF always tends to oppose the change. Okay? So what does this all mean? Well, if we get rid of this middleman, then this basically means that whenever the current changes through a coil, the coil will produce an EMF trying to oppose the change. Which means if you try to increase the current through the coil, it will induce an EMF and tries to decrease it. If you try to decrease the current, it will induce an EMF and will try to increase it. Remember, the coil has no problems with the current itself. Once the current reaches the maximum value, the coil does not induce any EMF. The coil is happy. It's the change in the current, that's where the problem lies. So whenever you try to change the current through any coil, it will induce an EMF and tries to oppose that change. And this ability to resist changing currents by inducing an EMF is often what we call inductance. And that's why coils are often called inductors. To be more precise, we should call it self-inductance, because the changing current and the opposition, they're both happening in the same coil. So the coil is sort of kind of like opposing itself. And that's why it's called self-inductance. So more inductance means more ability to resist the changes in the current. So it's kind of like an inertia. In fact, that's why inductance is often called electrical inertia, resistance to change. But change of what? Change of current. Now, before we get back to our story, let's think about how much EMF or how much voltage is this coil inducing due to the changes in the current. We can figure that out using Faraday's law. Faraday's law says that the induced EMF in any coil equals negative N d phi over dt, where phi represents the magnetic flux. You can call it d phi b over dt. This basically says that the induced EMF depends upon how quickly the flux changes. If the flux changes very quickly, a very high EMF is induced and it opposes the change in the flux. Now in our case, the flux is generated by the current. More current, more magnetic field, more flux. So we can say that in an inductor or in a coil, flux, magnetic flux is proportional to current. So you know what we could do? We can write this to be equal to negative di over dt. We're basically saying that the flux is changing because the current is changing, right? And it's proportional, so there should be some proportionality constant, and that constant we often like to call L. and that L represents the self-inductance. So this means if the current changes very quickly, the EMF induced is very high. If the current changes very slowly, EMF induced is very low. If the current doesn't change at all, no EMF is induced. And for a given change in current, a given rate of change of current, notice the EMF would be high if the inductance is very high. So if the L value is huge, it means very, very high resistance to changes in the current, very high EMF induced. If the inductance value is low or 0, notice it doesn't matter whether the current changes or not, there will be no induced EMF. So this thing represents the inductance. And very quickly we can work out the units of the inductance. Feel free to pause and try figuring out yourself. So the unit of inductance becomes EMF, which is volt divided by amperes per second. Divided by amperes per second, and the second will come on the top. But we often like to write this Henry, named after Joseph Henry, who was another person who independently discovered electromagnetic induction. And just like capacitances or resistances, which only depend on their geometry and the material used, and it does not depend upon the current and the voltage, similarly, inductance also only depends on the geometry, depends upon the number of turns, what is it turned around, the material used over here, but it does not depend upon voltages or currents. And in future videos, we'll see how to calculate the inductance of a coil or a solenoid, but it does not depend upon voltages or the amperes. With that, now we can get back to our original experiment. So what happens the moment I close the switch? Well, the battery says, hey, I want to increase that current from 0 to 1 ampere as quickly as possible. So there is a di over dt coming. And the inductor says, I hate changes in current. And so it opposes that change. And the way it does that is it induces an EMF, or it produces a voltage. And since it's opposing the battery because it doesn't want the current to increase, the voltage comes this way with a plus on this side and the negative on this side, which opposes the current. But then the battery says, all right, okay, I will grow the current a little slowly. So di by dt reduces. And as a result, the induced EMF, the voltage induced, starts reducing. Now note very carefully, I did not say the current reduces. The current is 0 to begin with. How can it reduce? But di over dt, the rate at which the current is growing, that slows down. The battery basically says, okay, inductor, I will increase the current a little slower. So the inductor gets a little less mad. And as a result of that, now the current starts growing. And as the current keeps growing, the di over dt starts reducing more and more. Becomes smaller and smaller. And as a result, this induced EMF starts becoming smaller and smaller. The opposition starts becoming smaller and smaller. And that's why the current can start becoming larger and larger. And that's why slowly and steadily the bulb starts glowing. And eventually, once it reaches that max value of 1 ampere, the current no longer changes. Di over dt becomes 0. And once that happens, there is no longer an induced EMF. The inductor is happy because the current is not changing anymore. Remember, inductor has no problems with the current. It's the change in the current that the inductor has a problem with. Yes, I'll keep saying it until you get it, because this can be confusing. Okay, and I hope you agree that if the inductance value was very high, if this was a larger inductor, then it would take longer time for the current to rise to its maximum value because the opposition would be so much stronger. Okay, so now the current is running at its max value, no longer changing. The inductor has no longer any effect on the circuit. And now I try to open the switch. What do you think is going to happen? Based on what we learned, can you pause and ponder upon this and think about what's going to happen if I open the switch now? All right, let's do it together. Let's open that switch. So far the inductor was calm. The moment we open the switch, the battery gets disconnected from the bulb and the battery says, let's get the current back to 0. And the inductor goes wild. The inductor says, are you kidding me? I hate changes in current. Now the di by dt is negative. The current is trying to reduce, and that too, it's an incredibly high value. The current is trying to go to 0 almost instantly. The inductor gets mad. The inductor induces a much higher EMF, but this time in the forward direction. Can you see that? Negative times negative becomes positive. So this time the inductor is trying to support the current. Remember, inductor never had a problem with current. It always has a problem with changes in the current. So the inductor tries to maintain the current. But wait, the circuit is broken. There is air in between. There's so much resistance. How can it do that? Well, it generates a huge EMF. A huge EMF is now coming. And as a result of that, it's trying to maintain that current. But wait, where would the charges go? The charges don't have anywhere to go. The circuit is broken. Because the inductor is pushing, the charges get accumulated over here. A lot of positive charge gets accumulated. A lot of negative charges will get accumulated over there. And eventually, there will be a spark. But the inductor can't maintain that. Eventually, di by dt goes to 0. This goes to 0. And the current dies off. That's the story. And during that last second when the inductor got really mad, the voltage that it generated was incredibly high. It can be hundreds or even thousands of volts. And therefore, it's incredibly dangerous to try and switch off a circuit where there are huge inductors involved. It can cause nasty sparks. And so that's the story of inductors. They hate changes in currents. The quicker you try to change the current, the more stronger EMF they tend to induce. And so one of their many applications is to maintain a steady current. If you have some devices which are sensitive to current changes and you don't want them, put an inductor in series with that. It'll take care of it. And we'll talk about more applications when we learn AC circuits.